Welcome back to PID Controllers, Intro to Control Design. In this lecture, I'm giving you a walkthrough of Assignment 3. Here you can see my solution to Assignment 3. Note, I used a maximum integrator windup of 5 and an output maximum of 2.5. Here's where I implemented a max integrator term to prevent integrator windup. Let's see how my solution performs with a people mass of 200. You'll notice that it's quite smooth, but it takes a little while to close those last few centimeters. If we turn on PID debug, we can see why this is. Note that the I component hits its max value, but its real value it needs to be at to hold up the people mass is here. However, the I component can't go down unless the error is negative. That is, we are above the set point. So the error has to go above the set point, so that way we can start reducing our I term so it can perfectly balance the people mass here. This is essentially a little bit of integrator windup. If I set the integrator windup term to something much larger, the elevator will hang at that up position for much longer. Ideally, you would want to set your max integrator value to the very max that you could want to encounter in the real situation. However, you generally don't have that much knowledge, so it's better to set yourself a little bit of breathing room. Now let's try in the down direction. Note that this is pretty equivalent to setting a negative mass with the same direction I had before. So you can see that the controller struggled a lot more with that one, because before it had to go from positive 1.25, the integrator term had to go from positive 1.25 to 1. Now it has to go from negative 1.25, because remember it's starting at the bottom, and then work all the way back up. If you had a lot of prior knowledge about this system, for example, you knew that the counterweight mass was always equal to the elevator mass and the people mass was always positive, then you could use integrator windup but not have it symmetrical. You could have a floor of the integrator at 0, so that way the integrator term would only have to go from 0 to 1, and it wouldn't hang so long in the bottom part there. Just for completeness, I'll show you that negative mass, but it's the exact same as what I just showed you. Again, the integrator term has to go from positive 1.25 all the way down to negative 1-ish. So if you had some better prior knowledge about the system, you could set a floor to the integrator. Now when you look at the different components, the P component, the I component, and the D component, from a coding standpoint, a PID controller really isn't that complicated. It's not that many lines of code. However, hopefully in this course you didn't just learn what specific lines you need to write, but you actually understand the logic and the reasoning behind them. Because not all situations will require a PID controller. Some situations might just require a PD, some just a PI, and some just a P controller. So I hope now that you've finished the core content of this course, you feel confident in your ability to not only create a PID controller, but actually understand what's happening in one and why. Like I said, that's it for the core content. Stick around for the next section though, where I'll talk about advanced controllers and actually war game a few PID controller scenarios if you were going to design your own for a certain environment.